Have you ever really stopped to think about what an AI sees when it looks at a photo? I mean, really sees. It's probably not what you're imagining. So let's dive into this, well, kind of alien world of computer vision.
Welcome to Super Courseva, where we break down AI, technology, and future skills into simple lessons.
Okay, so to really get how an AI learns, first you've got to understand this huge difference between how we see the world and how a machine sees the exact same thing. I mean, just look at this. It's wild. When you see a photo, your brain, boom, instantly recognizes a face, a person, maybe even someone you know, right? But a computer? It sees nothing. Zilch. No faces. All it sees is this gigantic grid of numbers, like a massive spreadsheet that has zero meaning to start with. And that right there is the big mystery we're going to solve today. How in the world does it bridge that incredible gap? How does it get from just cold, hard data to a confident, hey, that's Sarah, kind of identification? All right, so the answer actually starts at the most basic level. Every single digital image, right, is just a grid of these tiny little squares called pixels. Now, for a simple black and white photo, each pixel is just one number, how bright it is. But for a color photo, it's actually 3 numbers for every single pixel. One for red, one for green, and one for blue.
Okay, so pixels, numbers, got it. But now let's talk about how this simple idea snowballs into a truly massive challenge. It's one thing to say it's a grid of numbers, but it's the sheer scale of it all that makes this so mind-bogglingly difficult for an AI.
Let's put this in perspective. Think about a much simpler problem we might give a machine learning model, like, I don't know, predicting t-shirt sales. You might give it 4 inputs: price, shipping cost, marketing budget, material. Just 4 nice, tidy little data points. But for recognizing a face, how many inputs do you think we're dealing with here? Any guesses? Get ready for this. 3 million. Yup. For a pretty standard 1000 by 1000 pixel color picture, the AI is just flooded with 3 million individual numbers, all at once. That's the sea of data it has to swim through just to process one single picture. That is the insane scale of the problem we're talking about.
So, I mean, how on earth does any system make sense of that? Seriously, how do you find a face in a random jumble of 3 million numbers? It really does seem impossible, right?
Well, the solution is actually surprisingly elegant. You have to stop thinking of it as one single giant calculation, and instead picture it like a digital factory, like an assembly line that builds the answer piece by piece. So inside what's called a deep neural network, the data moves through these layers of, artificial neurons. Each layer has a very specific job. It takes the output from the layer before it and just makes it a little more sophisticated, a little more organized, one step at a time.
Okay, so here's how that assembly line actually works in practice. First, the 3 million pixels, they go in. The very first layer of neurons, it doesn't see a face at all. It's just finding simple edges, vertical lines, horizontal lines, little curves here and there. Then the next layer takes those simple edges and starts combining them into more complex shapes. Hey, that looks kind of like an eye, or a nose, or a mouth. Then a third layer takes those parts and assembles them into what look like actual face shapes. And only then, at the very end, can the system make its final guess. I think this is Sarah.
Okay, that whole assembly line thing is pretty clever, right? But here comes the most surprising, almost magical part of how this whole thing actually works. This is the bit that really blows my mind.
Just let that sink in for a second. Not a single line of code was written by a person that explicitly told the computer what an eye or a nose or a mouth looks like.
Right, we didn't code a nose detector. We didn't build a mouth detector. We didn't give it any rules. We didn't program it with human anatomy. We did none of that.
The AI, it figured it all out on its own. It's incredible. Just by being shown thousands and thousands of pictures of faces and being told the correct names over and over, it learned, it actually evolved the most efficient strategy. It discovered for itself that the best path from 3 million pixels to the right name was to first learn to see edges, then parts, and then whole faces. So this fundamental process, this whole idea, actually has a name. It's called A to B mapping. It's super simple when you think about it. We give the AI input A, in our case the 3 million pixel values, and we give it the correct output B, the name Sarah, and then we just let the machine figure out the incredibly complex connection that links A to B. That right there is the absolute core of most modern machine learning. All right, so now that we've walked through this whole journey from a chaotic mess of pixels all the way to a clean identification, let's just pull back for a second and boil this down into a simple, powerful blueprint you can take with you.
Okay, so what did we really learn? First, machine learning, at its heart, is just this simple idea of A to B mapping. Second, data science, well, that's the art of looking at that whole process and figuring out what useful things we can learn from it. And finally, deep learning. That's the specific technique we saw today. That's how we solve these incredibly complex A to B problems, by stacking all these layers of neurons together like Lego bricks until we can find a face in a sea of numbers.
And there you have it. You now have a foundational mental model, a real blueprint for how AI actually thinks and learns about these really complex problems. See? It's not magic. It's just a really, really clever, logical, layered assembly line that learns all by itself.
So you get the theory now. You understand the what and the why. But that just leads to the next big question, doesn't it? How do you actually take this theory and put it into practice? How do you build one of these systems for a real-world project? Well, that's what we're going to get into next time.